Hello, everyone. Last week we covered the fundamental theorem of calculus part 2, and I promised we're going to cover the fundamental theorem of calculus part 1 in great detail, in good details, this coming week on Tuesday. But I felt one we didn't do enough example on the part 2 application. So here, I want to take this opportunity to show you guys, okay, these things could be on your final exam, as how to show work, okay, because here you have lots of new notation, and there's one thing called an indefinite integral, and there's something called a definite integral. And what's the difference, right? Indefinite integral are antiderivative. In other words, if you look at this notation, let me bring up the notation. This is the notation for indefinite integral. And the definition for definite integral is that you would have a lower bound and you have an upper bound. Okay, so this is the indefinite integral notation. And of course, it's going to be on f of x dx. This meaning is to give the antiderivative of the function f of x. Okay, so we must understand the notation. And because we know that once a function has a antiderivative, it has many antiderivatives. So we add the constant, right? So here in this table, you can see that the way it's being expressed, right? The derivative of negative sine x, a negative cosine x is sine x. Therefore, and this is saying, give me the antiderivative of sine x, which is negative cosine. So negative cosine x is the antiderivative of sine x. And the antiderivative of cosine x is sine x. Okay, so when you see the notation written in this way, it's asking for the antiderivative of f of x. Now, how about the other one? The definite integral, however, is to find the area. The meaning is that is the area underneath the area, or you can say between the curve and the x-axis. Okay, so these two have entirely different meaning. They have entirely different meaning. So when we express it, we must express it properly. Okay, so for antiderivative, I'm going to put this table over here. Maybe make it smaller so you can see these references. And also at the same time, I'm going to find a picture to show you what is the these pictures, you've seen it multiple times, right? The area underneath the curve is what we are interested in while we are doing definite integral. Okay, so let's see if I can find a proper picture to show you that. Okay, the meanings are different. So this is the picture, and I think I'm going to bring it right in front of you. Okay, which is very commonly seen. Here we go. So this is a picture of a definite integral. Okay, so the two meanings are different. The two meanings are different. So I'm going to give you some examples. And this table have given you all the examples you wish. Okay, all the examples on basic functions. And take the example of say the first one, right, which is also very commonly seen. The integration, it's also called integrate, right? And indefinite integral. Suppose I have a x raised to the power of 2 dx. And we know its antiderivative is 1/3 multiply, x raised to the power of 3. And plus a constant. Okay, so here you need to understand that this piece, okay, of course, the constant c is any real number, is the antiderivative of x squared. So let that be an example. Okay, so example number 1. And takes another example, right? Example number, okay, the other example, I will put it for definite integral, right? For definite integral. So what I would like to show you in this case, in the case of definite integral, okay, in the case of definite integral, suppose we have a function, okay, so we're gonna have a function, and this function from 0 to 1. Okay, let's see which function we like to see, say e to the power x. E to the power x. Okay, maybe I would choose from that's okay. That's actually okay. Okay, this, by writing down this notation, the intention is to find the area underneath the curve. Okay, so I'm going to put this as example number 2, and then I'm going to elaborate on this one to see the full meaning of it. And the next one, of course, how do we express it properly using the fundamental theorem of calculus? Okay, so suppose we have this one, right? What does this mean? This means that we have the function e to the power x. Okay, and of course we can graph this function. We can graph this function, and I'm only going to view a piece of this function. I need more adjustment, right? So from 0 to 3, that should be sufficient. So I see this curve, right? Let me make a little bit more adjustment. So the area of our interest in this piece is just from 0 to 1, right? We're interested in the area between 0 to 1, right? So what is that area, right? So you're gonna, and of course we can find the area by the definition, which we've seen some examples. And so here, let me just show you in the concrete example. When x equals 0, y equals to 1, e to the power of x equals to 1. So that's one point there. Okay, so let me see, I should have chosen the point. There we go, right? Another point would be when x equals to 1, the e to the power x equals to e. So another dot. So between these two dots, right? These two dots, what are these two dots? These are the endpoints. The endpoints. So you have f of x. This is f of x. F of x is e to the power x. So by writing down this notation, so I'm just going to put the numbers in place, right? So you have f of 0 equals to 0. This leads to the point over here, this point. Okay, so that point is 0, 1, right? And next one, the next point, okay, is f of 1 equals to e to the power of 1. That equals to e. And the respective points is 1, e. So now what do we have here? Let's see. I'll put some arrows. Where's my arrow? Here. Okay. All right. So this point marked that one, and that point is being marked over here. And there's so between A and B, what is A? What is B? A is 0. Okay, this is A and this is B. So between these two numbers, okay, between these two numbers right here, let me make it thicker. Eraser, I'm going to just erase that piece and make it thicker. So this is the interval in consideration, right, between 0 to 1. And that's the curve. This is the curve, which is f of x. So this is the point, this is the one endpoint, this is the other endpoint. Okay, and the area of our interest, because we know that we want to find the area underneath the curve or the curve between the curve and x-axis. So what is the area? The area is this piece from here, here, all the way along the curve. That's all of it. Okay, so if you just shade, that's the area of interest. So when we write this notation, we are interested in the area underneath the curve. You can see the meaning. One is to find antiderivative, and the other one is to find the area between the curve and x-axis. Okay, it's very important to understand this notation. Once you understand this notation, and then next is, what does the fundamental theorem of calculus say? Calculus part 2 says. The calculus part 2, fundamental theorem of calculus part 2 says that you just have to find the antiderivative. Okay, so in that case, the antiderivative of e to the power x, right? So suppose we want to find if I can find the antiderivative e to the power x. So antiderivative of e to the power x, okay? You can say the word antiderivative of e to the power x. You can also write it down in this notation as e to the power x. And that's another way to say the antiderivative of e to the power x. And what is it? It's e to the power x plus all the constant, right? Because we know that e to the power x has many, many antiderivatives. And the fundamental theorem of calculus part 2 says all you have to do is pick up one of them. Okay, there's all these antiderivative as you choose different c, right? C can be any real number. You just pick one. Well, how about I just pick the one when c is 0? right? That's one of it, one of the antiderivatives. So suppose I'm taking the e to the power x. I'm going to call that antiderivative. I even give a name to that antiderivative, f of x. Okay, f of x, capital F of x, actually is a family. It's a family of x, right? So we can use, you can use this notation, but when I choose, I'm going to choose my capital F to be one of it. To be one of it. Okay? One of it, you only have to choose one of the antiderivative, which is the simplest one, right? And I'm going to choose e to the power x. I'm going to choose it to be e to the power x. And then what I do, right? So I have the lowercase f, which is set in the theorem, and I have uppercase capital F, which is the antiderivative of the lowercase f of x. And the fundamental theorem of calculus part 2 says it equals to, you just take this capital F of x and you evaluate it at the endpoints, f of 1 minus f of 0, which is the f of b minus f of a. And in our case, b is 1, a is 0. Once you understand these, the next is how do you express it properly? How do we express it properly? Okay, so we understand this situation. So one way to express it is that, well, I already know the antiderivative, right? I already know the antiderivative. So I can just write it down as e, okay, e raised to the power of x. Okay, the common way of expressing it, you can see e to the power x. Okay, I'm going to put a bar here. Okay, e to the power x, which is saying this is the antiderivative. I'm going to evaluate the antiderivative at the lower number, which is 0. The higher number on the other end of the interval is 1. So this is a common expression. So this is a function, and that's the antiderivative. And that is equals to, with the capital F of 1 minus capital F of 0. So this is the notation. And of course, in notation, in our case, we just e to the power of 1, subtracting e to the power of 0. Okay, I choose an example where the antiderivative and the function itself are the same, but for a constant, right? So this is a special case. So e minus 1, that's the answer. Okay, so that illustrates the notation, okay, and the meaning between indefinite integral and the definite integral. All of these formula, basic functions, antiderivative can be used. They're all at your disposal. You can bring them with you during the exam, but you have to, and because we like to use these formula sheet and these flashcards, we have a higher expectation, on the other hand, that you should express the work properly. Okay, so this is one of the reasons for this recording, is that I want you guys to get started practicing. Okay, so example number 2, that's how you do it. That's really how you show your work. That's really how you could show your work. And do you need to do all of these pictures? The answer is no, you don't have to, but you need to understand it. You need to understand it. Okay, so let's take another example. Example number 3. Okay, and this time I'm going to, I wish you to look at the homework for week number 15, which is coming up, which is starting from, actually, you can see the start today, right? So start practicing today, please, okay? start practicing today. You're gonna need this for the next course. So I'm going to give you guys a head start. I'm gonna take one of the questions from your homework. Okay, to show you how to show work for indefinite integral and definite integral. Okay, suppose the question is asking you just to find the definite integral. We're integrating from 1 to 9. Okay, I'm going to use this function. Wait, it's like, it looks like it's more like 1 to 8. Sorry, 1 to 8. That's a definite integral. 1 to 8. Okay, x raised to the power of negative 2/3 dx. And we understand this is to find the area underneath the curve. And what you do, how do you still work? You can use this formula, right? And you can choose 0, c equals 0, because the fundamental theorem of calculus part 2 that you only need is one of the antiderivative, right? And now the antiderivative is, we can follow this formula, right? N equals to negative 2/3. So we're going to do 1 plus, well, n plus 1, 1 plus n, negative 2/3. Okay, I'm basically following the power formula. And x raised to the power of the same number, really. Okay, I'm just going to copy and paste. You don't have to write it the way I do, but you do need to express, you need to have this bar. Okay, from 1 to 8. So the lower bound is 1, the upper bound is 8. Okay, so you have a bar next to it. Or you can have the next step, which is to simplify. You can go there directly, because 1 plus negative 2/3, that's going to give us 1/3. 1/3, right? So this number could be replacing this 1/3. So you can skip that step. You can skip this line completely and go this line, right? And you can even simplify this as 3. But you always have to have this piece attached to it, because we're looking for definite integral. And last but not least, then you're gonna, when you show your work, you're gonna write it down as, I will leave out the 3, I only evaluate this part. So I'm gonna put a parentheses, and that's gonna take me x raised to the power 1/3. Evaluate when x equals to 8. I'm applying fundamental theorem of calculus. And the next one, I'm going to apply f of a, capital F of a, right? So what I'm applying here is what the theorem says, capital F of b minus capital F of a. So that's what I'm doing. So that's considered the proper application of fundamental theorem of algebra, of calculus part 2. And then you simplify. Okay, so you have 3, and then in parentheses, a to the power 1/3, 8, that's going to be 2. 2 minus 1, the final answer is 3. Okay, so make sure you learn this, how to use this notation, And you can get started doing the homework for week number 15. I know you have you don't have a lot of time left before the final exam, but some of these questions will show up, and we're going to teach you more how to do integration. And you need these It's all about applying fundamental theorem of calculus part 2. And I'll applying part 1, I will make another recording. Okay, so let's look at another example. Let's look at another example. Other examples such as, I'm going to choose a somewhat maybe harder one and the even number one, right? So look at this piece. We have a example number 4. Okay, that's my example. I'm going to choose a function which has trig function and also has exponential functions. Okay, but it's a definite integral. It's from 0 to 3. 0 to 3. From 0 to 3. Okay. Is 2 times sine of x subtracting e to the power x dx. Okay, so we are to find the area under the curve. We are to find the area underneath the curve. If you want to you want to know the meaning of it, of course, you can graph the function, find the endpoints, all of that. But we don't need all of that stuff, right? Just for let me just get straight to the work that you need to show and how to show it. Okay, here we actually use the sum or difference of integration, f of x plus g of x, or you can, if it's subtracting, it's the same, right? We have talked about these properties. And there's also 2 times sine x. So when you do the integration, you can use these properties, right? For example, you can write it as this integration sign, you're gonna bring it to it, right? And so it's a 2 times sine x dx. Okay. One of the common mistakes I remember people, my past student makes is that they forget to write dx. Okay, small mistake, but it could cost you points. You can write it this way and bring the 2 outside. So I'm using this property, right? Bring the constant outside, so I can bring the 2 outside. So then you apply fundamental theorem of calculus part 2 to each individual one. Okay, and how do you show your work? How do you show your work? So here 2, the antiderivative sine x is negative cosine. So you're gonna write it down. Okay, you can either write it negative cosine x or bring the negative sign in front of it. Okay, you can write it that way. And this piece will be evaluated at lower bound 0, upper bound 3. You can write it that way. Subtracting the antiderivative e to the power x, of course, we know that that's e to the power x. When we evaluate it, lower bound at 0, upper bound at 3. Okay. Now, then we're going to work it out, right? Work it out. So here, this negative sign can join the 2, so we can have a negative 2. So then I would just do the evaluation, which I'm going to write cosine 3 subtracting cosine 0. Subtracting, here there's a minus sign here, so to be on the safe side, I'm going to put a bracket. So this is going to be e to the power 3 subtracting e to the power 0. And then you simplify. By the time you are in calculus 2, you are expected to know how to do all of these and show work properly. So cosine 0 equals 1, subtracting e to the power 3 plus e to the power 0 equals 1. Okay, you can do a few more, miscellaneous simplification, but you can just leave it as negative cosine 3 plus 2 minus e to the power 3 plus 1. We don't want to see decimal numbers. You're not allowed to use calculators. Okay, so don't worry about getting one single number. The only thing you can simplify here is just it's going to be plus 3. It's plus 3. Okay, this answer is perfect. We don't need to see the decimal numbers. Most of your professors, I promise you, they don't care about that decimal number. That actually you might annoy them by doing that. Okay, so you do that extra work of punching in the calculator, and this is, I'm sorry, most of the time it's probably not really appreciated. Okay, I'm just telling you the truth. Okay, I'm just telling you the truth. Anyway, let's look at another example. Let's look at another example. About using the properties of integration, right? We talk about these properties integration, and you even see the flashcards of them, right? We talk about, but we just didn't do much of the example. So here I would like to use this opportunity to go over some examples. Most of the coverage of these materials, your professor probably expects you to do a lot of homework. They don't have time to go over everything, and especially these considered algebraically, it's expected you guys know how to do it after we give you a couple of examples. But knowing that many of us have some deficiencies in algebra, so I want you guys to get started, practice how to write it down properly, because next week, as I'm talking about integrating by substitution, the notation could get even more, interesting, get even more interesting. That's all I can say. Okay, let's take this example. This is the last question on number 2 from homework number 15, which require us to view some properties. Okay, so example number 5, I'm going to put this as, I'm going to integrate, this is a definite integral again, and the boundary is from -2 to +2, and the function, we just give you a function, but this function is a piecewise function, and we want to find the area underneath the curve. Okay, and then it tells us what the function is, where the function is. Okay, so hold on. I can use more space, right? I can use more space. So this function has 2 pieces. There we go. There. There are 2 pieces for this function. And if x equals 2, oh, I should add a column. Okay. It's equals to 2 if it's between -2 and 0. Okay, And the other one, the other piece is that it's going to be a function 4 minus x squared. If x is between 0 and 2. 0 and 2. Okay. If we want to look at how these functions look like, let me see if the software will plot it for us. Right. So I'm going to, in most of the cases, I can expect some nice things from the software. There we go. So we got it. We got it. Okay. So I'm going to, we're going to come back to when we need the, so when we need the flashcards. Okay. So here, we got a graph. We got a graph. The graph, let me make some adjustments. There, okay, it's between -2 to 2, and the numbers on that. So this looks better. It's the area is from -2 to +2. Okay, so the area underneath the curve. So on this part we have a rectangle. On this piece we have a curve, right? We have a curve. We want to find the area underneath the curve. Okay, but we have two pieces. So how do we find the area on the curve, and how do we express it properly? How do we express it properly? Okay. When you're doing this actual calculation, you don't really need to see the graph. Okay, but you know there's two pieces. There are two pieces. And how do we still work? Okay, on this part, we're going to be using one of the properties we talk about is that there, it's on the flashcard. Wait, there's A, B, C. Oh, this one. Okay, this piece. I'm going to bring it over here, make it larger. It's almost invisible. I might have put too many things in one piece. Okay, so this property, maybe you like to make it a separate part. This property, right? So you can see that you're looking for area between A to B underneath the curve, but there's two pieces. So from A to C, C to B, typically C is between A and B. And this will be the property we can apply. Okay, so we're going to do this. We're going to do that piece from -2 to 0, right? Plus from 0 to +2. That's how you write it down properly. You write it down properly. And then once we have this separation, in the first piece, right, you're going to substitute the function. Just the function from 0 to 2 is 2, right? And the other one is 4 minus x squared. So you're going to show your work. So this is 2. Adding, and the other piece is added, right? So on this piece, the function is a 4 minus x squared. I think so, or 2 minus x squared. Let me double check. 4 minus x squared. There you go. So that's how you show your work. That's how you show your work. Okay, we don't need this table. We don't need this table anymore. And you integrate it. You have to show your work properly. Okay, so you're applying. So this 2 is a constant. You can bring it out. You can actually bring it out if you wish. You don't have to. Right? We know this is the area underneath the curve. You can leave the 1 here. bring the 2 outside. And so on this piece, by fundamental theorem of calculus. Okay, let's continue. We have one integral, and it's been written in another 2 integral on 2 smaller intervals. And then how do we show work next, right? So we just write it down like that. And the antiderivative of 1 is x, right? So we're gonna have 2 times x. And if you like, you can write it down. The lower limit is -2, the upper limit is 0. Adding, on this piece, you can separate it or you can put them together. Okay, there are multiple ways to write it, but the way I show you is just one of the ways, but you just have to make sure you use the notation properly. And on this piece, you can actually write it down. Okay. Let me write another row. You can write this piece as 0 minus -2. It must be minus -2, okay? Because it's f capital A minus f capital B. So it's just be reminded, it's a capital antiderivative evaluated at B minus antiderivative measure evaluated at A. Okay, so that's why it's 0 minus -2. So you can go directly here. So now let's look at the next step. You can write it together. The antiderivative 4 minus x squared, you just find the antiderivative for each. Okay, you can separate it if you want, but here I'm just going to write together. Okay. Let me separate it. So I will show you. Okay, I'm going to show you the separated case. Separated sometimes is cleaner. Okay, so that's one. Subtracting another one. Right? So you write it this form. We just had this thing taken care of, right? And then it's the next one. Or you can actually, but can you combine 2 and 4? No, you cannot, because there are different intervals. And you can even bring the 4 outside, like we did before. So here you're just going to have 4 times 2 minus 0. 2 minus 0 is 2, right? You don't even have to write the 0. Subtracting the antiderivative of x squared is 1/3 of x raised to the power of 3. And that's evaluated a lower limit at 0, the upper one, the upper end is 2. Okay, so they follow pretty much the same pattern. And here, if you like, you can write it down. Oops. You can write it down as such. Okay, so over here, this will become 2 to the power 3 minus 0 to the power 3. Okay, some of this work can be simplified here already. So here you can already simplify, that's going to be 2, right? And this piece is just going to be 2. And last but not least, you have 4 plus 8, that's 12, subtracting 1/3 times, that's 8. That's an 8. Then you just do some reduction. Common factor, the common denominator. So in the end, you give a final answer. So you always have an area underneath the curve. Should that be asked, you're integrating that kind of function. The common denominator here, you can write it as 3 under 36. That should be a piece of cake for you guys. So let me just finish it up. 3 So 36 minus 8, that's 28. That's finished. So that's some of the examples of following the fundamental theorem of calculus part 2. What can be done, right? The new notation, the difference of notation. So one more. I think I will do one more with you. Okay. One more or two more. Number 30. This is number 30. Yeah, example number 5. The integration of a function on interval from -1 to +2. And the function we have here is 3u minus 2 multiply u plus 1. And don't forget to write the du. Okay. Algebraically, you can just go straight to it. You can just go straight to it, and you would FOIL. Okay, you would FOIL. I don't worry that you guys know how to do FOIL, but I like to show you how to show your work properly. Don't drop anything. Don't drop anything. Okay. So while you're foiling, feel free to use a scratch paper if you need to, right? Then you get 3u squared. 3u squared plus 3u minus 2u. So that's going to be plus u minus 2. Okay, make sure you FOIL it properly. Right? And write it down line by line properly. Maybe leave a line in between. And the next step, you can either separate them. You can separate them, or you just do them all together. Okay. So this I've done this separately before. So let's do this all together. So the antiderivative of this entirety things in the bracket is going to be u to the power 3, right? Plus u squared divided by 2 minus 2u. And evaluate at 2 from -1 to 2. Wait, sorry. Wait. Over here, -1. Okay. And then you just plug in numbers. You just plug in numbers. Okay, so this bracket subtracting another bracket, parentheses, sorry. But with this first one is going to be all substituted by 2. And these are all substituted by 1. You can do it, you can write it down this way. And then simplify, right? This is 8. You can do the rest pretty well. So this is a 4, right? This is a 4. 4 minus 4, that's 0. So we have 8, right? Minus on this piece, you have 1 minus 2. So it's -1. There's a negative sign in front of the plus 1 and minus half. Minus half, so you ended up adding a half. So the final answer is just 8.5. Okay. Let me do one more though. There's one uses the antiderivative of arc sine. Okay, so this will be the last one. So example number 7, I believe, or 6, sorry. The integration of, it's a definite integral again from 1/2 to, so 1/2 all the way to 1/√2. And the function we are integrating is 4 over square root of 1 minus x squared dx. Okay, make sure you express it properly. In this case, right, the integration can be expressed. The 4 can be taken out. Okay, can be taken out like that. And the antiderivative of 1 over square root of 1 minus x squared, that's arc sine x. So the antiderivative, right, so that's going to be the antiderivative. So you can just write very little step. Arc sine, whoops, my bad. Arc sine of x evaluated at these two endpoints. The lower endpoint is half, and the upper endpoint is 1/√2. If you even want to skip this step, you just write it down as arc sine of 1/√2, subtracting arc sine of 1/2. Okay, you can skip this one. This is optional. There are a lot of optional steps in between, but anything you express, it should be nice and clear. All right, so it's about the last step. We got, and of course we know the answer here. This is the answer. This one equals to pi over 4, right? Arc sine of square root 2/2, and the other one is pi over 6. Okay, and you are certainly expected to simplify this, right? So you can multiply 4 inside, so you have a 4 minus 2 pi over 3, and so in the end is pi over 3. There you go. Okay, so in this lesson, we primarily showed you how to show work properly and difference between indefinite integral and definite integral, and understand how to express work properly. Okay, so thank you for watching. Until next time.